All right, welcome back. All right, so right before we left, we showed our correlation function, and again, how we've shifted between our two frames, some location to the right. So now our next bit of code, the objective is to determine where this location is of maximum intensity, and ideally the subpixel resolution. So instead of saying, well, it's only 5 pixels, within better that, using fitting algorithms, can we get a centroid location? And to do this, we're going to rely on some code that was written by John Crocker, David Greer, and then transcribed by Eric Dufresne, that probably 10 years ago, for particle tracking. So there are 2 different functions here. And again, I'm going to link them in chat for everybody. But it's this pk find and this centroid. And so what it does is pk find looks through an image and tries to calculate what the, actually I think he has a description here somewhere. It looks through an image and for bright spots compared to a dark backgrounds, and tries to determine where those peak locations are to single pixel resolution. And then the centroid code then takes that and calculates the subpixel resolution of the peaks given by the peak code. So we're first going to run this pk find to determine those peak locations to pixel resolution, and then feed that into the centroid code to determine the subpixel resolution of these imaging peaks. All right, so we're back to our script file here. All right, so to do this, we're going to first add one more step before we throw it into the peak finding function. And what we're going to do is we're going to think about the case where our peak location is at the very edge of our frame. If we try to throw this then into our peak finding function, it's going to run into an error trying to determine an area around the edge. It's going to look for values that are elements of an index of, let's say, 17 in its column. So to get around this, we're going to use the function pad array. And again, this is just a built-in Matlab function. And what pad array does is just add a buffer around your image of 0 values. So if we do pad array, the first input is just the image or the matrix we were interested in. In this case, it's going to be our correlation function. And then the pad size, or the size of zeros you want around the kind of the border of your matrix. So for us, we're just going to keep it simple and just say the box size. And again, we're doing it twice here to say, well, we want to add in zeros in our X direction and then in our Y direction as well. And we're just going to resave our correlation function with this pad array around it. So again, if we take a look at the image, we can now see that we've created zeros all around our frame that are, in this case, a box size, then our image, and then another box size to the right. And again, this is just to help the peak finding code determine what the peak locations are if you have a peak that's close to an edge. Okay, so now we're going to use our peak finding function, pkfnd. If we read the notes that, I guess Eric Dufresne wrote this version of it, left us, the input here is the image we're interested in, the minimum brightness of the pixel in order for it to be a local maxima, and then the size of the kind of the region that we're interested in. So we'll go back to our code here. The image we're interested in is our correlation function. The kind of maximum relative intensity, we're just going to label as 0.1. And for our size, we'll do box size over 2. So there is some kind of play with what you set these values as. I'm choosing these values based on a little bit of just kind of the pre-work that went into this lecture of finding something that works well for this image. But again, if this is your own data set, kind of tweaking these values for your peak finding could also kind of improve the performance of your PIV code. All right, so we're gonna just go ahead and run this, and we'll see we've returned 3 different peak locations at 2919, 2932, and 3035. So this is our single pixel resolution of our peak locations. And we can now say, well, let's use the centroid code. Again, the same thing. If we take a look at the function itself, we can see our inputs here are the image we're interested in, the location of the maxima from the pk find function, and then the size, or the kind of the region over which we want to search within or near that peak to determine the subpixel resolution. And then this also optimal parameter. We're going to ignore that for now. So if we go back to our code, again, our image that we're interested in is our correlation function. We are interested in our peak locations from pk finds, or pk. And then our last, we're going to say we want to search within 5 pixels around that peak location to determine the peak to subpixel resolution. All right. So we go ahead and run it, and we can see, well, previously we said our peak was at 29 and 19. Here, the first peak, we get subpixel resolution, as well as this third value here is the intensity at that peak. So the highest value in our third column should be the maximum intensity, or the kind of the highest peak location within our entire correlation function. So in this case, we expect it to be at about 3025. We go back to our correlation function, 3025, it seems appropriate, right? That's about where we might guess our peak location is based on just the color graph. All right. So now our next little bit of code here is just going to be, we want to find the brightest peak location and save that data. Okay. So we can do this by saying, well, we just want to know the maximum value of our centroid location within that third column. And what we can do here is we can just say, well, this should be the value and this should be the index location. So what this will do here is it'll return both the maximum value and the index location. Really, all we care about here is just that index location. We want to know that the maximum brightness is in the third column. And then we can say that the centroid we're interested in is going to be the values at that, I'm sorry, this index would be the third row. So the values from that third row, we want all those values as our output centroid. All right. And then finally, we want to save this information and we want to export it out of our matrix as the XY location. So we're going to define one final variable here. We'll call it display X. And this will be at row location and column location. So again, remember, the row and column were the kind of the index location of our region of interest we're interested in. So we're going to save that as our centroid location, or our centroid out value. And then for our X, it's going to be the first row. And same thing for displacement out Y. In this case, it's going to be the second row. However, you remember we added in our pad array up here. So our actual values for the centroid location are shifted by our box size. So what we can do is subtract out the box size it's this entire little function here. Yeah, so this will center our kind of our displacement value over 0. So we're subtracting out the box size from the pad array, and then this box size divided by 2 plus 1 that corresponds to kind of the shift from this location here to the center of our box. So now our displacement out here should be the centroid location relative to the exact center of our box. And then the same thing for our Y outputs. All right, and now there's one more kind of correction we have to do. And that is when we're doing the correlation function, just the way that Matlab goes about it, is in the opposite direction of kind of how the values have shifted. So instead of, our maximum peak location here is to the right, it's actually to the left. So we're just going to multiply everything by -1. And this just arises based on how Matlab goes through the matrix to calculate the correlation function. Okay. So now we have our output display in the X and the Y. And I believe that should be it. So now we should be able to run. We're first going to save this real quick. Week 3 example. So we've run our code, and now our output, which was the display X and display Y, you can see is a 28 by 28, which corresponds to the center location of each one of our boxes. And it tells us how much we've shifted in the X direction and in the Y direction. So the last bit of code that we need here is just to combine all this information and plot it on top of our original image so we can get that nice visual of which way our image is flowing across the frame. So we'll write that real quick. So what we're going to do first is we're going to create a mesh grid of the center locations of each one of our squares. So you can think of this again as, call this X. X is going to go from 0 to the size of the number of squares we have. So yeah, I believe that's right. Yep. Right. So we're gonna go from 0 to the size of our matrix, and then we're gonna multiply all of this by our spacing. So now you expect, if we go from 0 to the number of boxes, it's kind of what this is telling us here. All right, so we have 27 boxes in our X direction. Our spacing, 1, 2, 3, 1, 2, 3. There we go. Our spacing will now kind of spread them out over our X direction, and then we're just going to add in that original shift by half our box size. So that way our center location is at 0. So we look at X real quick. You can then see, we're at 8, and then we have 6 pixels before the next center of our box, and the same thing for Y. We're going to do the same thing for our Y locations. So for this time, we're going to do the size of the number of rows. And then we're going to use the function mesh grid of our X and Y vector. And what this will do is we'll create matrices, in this case X2 and Y2, that are kind of the mesh grid of X and Y. So I think the easiest way to do is just kind of, we're going to run it. And we see X2 is now our X repeated over and over again through our Y, and our Y2 is the same thing, but now the same column instead of the same row. So we think about this as kind of our grid along our matrix of our region of interest. If we choose let's say the 1, 1, or let's say the 1, 5 square. In the first column, or the 1, 5, the X location is 32, and the Y location is 8. All right. So finally here, we are going to plot our image. So we'll do our first frame here. Image, there you go. So there's our image. We're going to turn our hold on, and then we're going to use the function quiver. And quiver is what lets us plot those arrows. So quiver asked us for our X and Y locations, and then the U and V are kind of the translational distance of where our arrow goes. So quiver, we're going to use our mesh grid X2 and Y2. So that's going to give us the center of each one of our regions of interest. And then we know from our loop up here, display X and display Y are the magnitude or the direction in which we've shifted between frames. All right. Now we can see the kind of the arrows that popped up here. I'm going to add in just our modifier R, so it should make the quiver red on top of our image. And one more if we do color map gray, we'll convert the image into grayscale. So that way it just pops a little bit easier. And there we have it. We've used our autocorrelation functions to compute the displacement within our image of where, or within our region of interest of where we're most correlated in the next frame. And we've plotted that kind of the map on top of our image. So this is the very first step in creating our PIV. And we're kind of out of time for today. So on Thursday, we'll walk through how we can then apply this to an entire stack of images to create our full loop. But does anybody have any questions on what we've covered today? Cool. So yeah, the other thing is I think some of the other topics we've talked about covering, including DDM, and some of the other kind of dynamic image analysis steps really are built on what we learned today in the correlation function. So computing correlation function between two images, you can imagine it trying to figure out what the mesh size of a frame is, or what the kind of the defining length scale of an image is based on how correlated it is with itself as you shift it across. So I'll try to find some examples of that we can also walk through, just so everyone has kind of a good understanding of the correlation analysis. But otherwise, thank you for kind of attending today, and I will, I guess, talk to you guys again Thursday at 11. We'll do the second half of this.